Our main research topic is reinforcement learning with human feedback for language models with proximal policy optimization. I will give a quick introduction to language models, followed by reinforcement learning with human feedback. Then we will discuss the precursors to PPO and NPPO. Lastly, we will talk about our experiment results. A quick introduction to language models. A language model is a probabilistic model that assigns probabilities to a sequence of words. For example, here, given the prompt that Shanghai is a city in, the language model is going to predict the next token or the next word. And the probability for each token indicate how likely a token is the next one. For example, here, China is the most possible tokens. But what's the relationship between language models and reinforcement learning? Think about in traditional reinforcement learning, the Great Wall example. Here, the agent is the robot that's going to move around the grids. And these are the reward, either positive or negative. And the policy, how the agent is going to move around the grids. In language model, the agent is the language model itself. And the state is the prompt, or we call it the input tokens. And the actions of which token is selected as the next token. In terms of reward, the language model should be rewarded for generating good responses and should not receive any reward for generating bad responses. In terms of policy, the policy actually is the language model itself because it models the probability of the action space given the current state. So let's take a look at this example here. Given the current state that Shanghai is a city in, the language model is going to predict the action, which is also the next token. If it predict the correct China, it will receive good reward. On the contrary, if it predict pizza, it will receive a pretty bad reward. So in a nutshell, reinforcement learning from human feedback is using reinforcement learning to directly optimize the language model with human feedback. But the question is, which reinforcement learning method to use?
The motivation for our research project stems from the wide release of various GPT models and the way they are trained, in particular, OpenAI's GPT-4. As we have learned from class, policy gradient algorithms have many advantages, such as their ability to handle continuous action and state spaces and guarantee convergence to a local optimum. They also have several disadvantages, such as high variance and sample inefficiencies. Proximal policy optimization has become a popular RL algorithm due to its ability to minimize some drawbacks of other policy gradient methods. When coupled with RLHF, a more robust solution to the agent learning problem becomes available. OpenAI currently uses a combination of these methods to train its GPT models. RLHF is a technique where the RL algorithm learns from human-generated rewards. This helps determine or reshape the reward function, which in many cases is difficult to do. RLHF's goal is to train the agent directly and not to determine the optimal policy. Some advantages of incorporating RLHF are the ability to handle noisy feedback and its efficiency with sparse rewards. In many cases, rewards are not given at each timestamp, and it provides stability while the agent is taking exploratory actions by allowing a human to correct early. There are two versions of RLHF, human in the loop and with human input only. To the right is a generic actor-critic algorithm based on the Bradley-Terry model that has human-only input. This model is used in pairwise comparisons. For example, is A more preferred than B? A quick walkthrough this algorithm shows that we are generating queries through past experiences, updating the answer to those queries, to those questions from the human, updating the reward function based on the responses from the human, and then updating new questions that are generated from the current policy, and then we update the actor and critic models. Here are some of the common types of feedback with RLHF, comparative critique and intertemporal feedback, which is giving small rewards in the pursuit of a larger goal. And some of the challenges with RLHF are the fact that human feedback is time-consuming and expensive, and that there could be potential bias with limited data.
Now I will introduce TRPO and PPO. They are both policy gradient methods which directly optimize policy parameters to mathematically predict return using gradient ascent. First is TRPO. TRPO introduced a key innovation. It refined the update process to ensure that these changes are stable and fall within a defined region. One of standout features of TRPO is its use of KL divergence to ensure stability and safety. TRPO also gives us theoretical guarantees on policy improvement and minimize the risk of making updates that could make the policy performance worse. Instead of using complex KL divergence constraints, people introduce clip probability ratio. This clip stops the computer from changing its strategy too much. So PPO offers several key advantages. First, unlike TRPO, which involves second-order optimization methods, PPO only use first-order optimization, which makes computational less intensive. Second, PPO reduce the computation overhead compared to other methods by streamlining computations. Last, PPO uses clipping in the objective function. This clipping method simplifies the implementation and reduces the likelihood of errors. Then let's talk about the details about the PPO algorithm. The main goal of PPO is to improve the way policies are updated in learning environments, ensuring that these updates are both stable and efficient. This formula represents the clipped objective function in the PPO. It calculates the effective value of the minimal between the probability ratio of the new policy to the old policy times the advantage, and the clipped value of this ratio. So the first step in the PPO algorithm is data collection. We execute the current policy within our environment to collect the essential data. This step is all about gathering enough examples to learn from. Next step is advantage estimation. We calculate the advantage of each action taking the calculated states. The advantage tells how much better or worse an action is compared to the policy average action. This step is important because it informs us how to modify our policy. Then we optimize the clipped surrogate objective function. This step is done several times to fine-tune the strategy without making big changes. In the final step, we update our policy parameters based on the optimization step. And we will repeat all the steps until the policy network converts to a satisfactory solution. Overall, PPO performs well within the limitation and demand of RLHF.
You may wonder how RLHF is exactly implemented. Given a prompt input from the dataset, the text Y is generated by the current iteration of the fine-tuned policy, concatenated with the original prompt. The text is passed to the reward model to return a scalar reward, indicating the quality of the generated output. Finally, the update rule is the parameter updated from PPO that maximizes the reward in the current batch of data. Note that PPO is on policy, which means the parameters are only updated with the current batch of prompt generation pairs. As mentioned by our teammates, PPO is a trust region optimization algorithm that uses constraints on the gradient to ensure the update step doesn't destabilize the learning process. We trained the reward model with 151,000 scored conversations. All models are based on Llama with 65 million parameters, a medium-sized language model. Now, we would like to show some demo from our model. As you can see, the generated sentences before the training are related, means informative and illogical. However, after training, the generations might be misinformative because the language model hasn't learned enough knowledge. But at least the generations are logical and related to the questions. In the future, we will systematically analyze the results with downstream tasks. We will apply different training data for a real-world model to figure out how PPO can be influenced. We may even try other reinforcement learning algorithms to replace PPO.